Good evening, everyone. In the first video, I discussed all the aspects of the electric field, electric forces, electric charge, and capacitance. In this video, I will briefly go over numerical examples to make the concepts of electric forces, electric fields, and electric potentials and capacitance clear for you. I understand that some of the students have not taken electrostatics in the school. This is why I would like to give more emphasis on these concepts. In this example, we have two charges, Q1 and Q2, located on the x-axis, separated by half meter. Q1 is minus 8 nanocoulomb, Q2 is 4 nanocoulomb, and we have a point P. Point P is at a distance 20 centimeter from Q1, and we have a Q2 which is 4 nanocoulomb at a distance 30 centimeter from Q2, and then I ask you to find the net electric field at point P. If you calculate E1, you will find that it is 18 times 10 to 2 Newton per coulomb, pointing in the negative x-axis. If you calculate A2, you will find it to be 4 times 10 to 2 Newton per coulomb, again pointing in the negative x-axis. As I told you in the first video, that the electric field at a given point due to negative charge appears as coming to it, while the electric field due to a positive charge at a given point appears as leaving it toward the point. So the net electric field in this case will be E1 plus E2, and since they add up, so the direction will be the same, negative x-axis, and if you add them up, you will get 22 times 10 to 2 Newton per coulomb in the negative x-axis. Here, a practice problem for you. We have two protons. Each has a charge 1.6 times 10 to minus 19 coulomb. The first proton is located on the y-axis at a distance of 2.56 meter from the origin, and the second proton is located on the x-axis at 2.56 meter from the origin. And then I ask you to find the net electric field at the origin. Now let us take the concept of the electric potential very quickly. The electric potential at any point in the space produced by a point charge Q is given by, so if we have a charge plus a Q, and we have a point P at a distance R from the charge, and then I ask you to find the potential at the point P, simply you just multiply K by Q over R, and since the potential is a scalar quantity, it is different than the way we calculate the magnitude and direction of electric field. So simply here you find the number, so you just multiply K by Q over R, and if the charge is positive, then the potential V here will be positive, and if the charge here is negative, the potential here will be negative. So if we have two charges, Q1 and Q2 along x-axis, Q1 is minus 6 nanocoulomb and Q2 is 4 nanocoulomb, separated by half meter, and we have a point P 20 centimeter from Q1 and 30 centimeter from Q2, and then I ask you to find the potential at point P. Of course, V1 due to Q1 will be negative, and V2 due to Q2 will be positive, and if you calculate the net or total electric potential at point P, you will find it to be 150 volt. Again here, we have two protons. One is along Y, located at a point along Y, and the other is located at a point along X. They are equidistant from the origin. The distance is 2.56 meter, and then I ask you to find the electric potential at the origin. So you do it yourself. For continuous charge distribution, continuous charge, we mean by continuous charge distribution is that the charges are closely spaced on the surface of a given body, and such that we can consider the charge distribution as continuous. So we could distribute the charges along a line, and in this case we calculate what's called linear charge density, Q over L, and the unit of the linear charge density lambda is coulomb per meter. We could distribute the charges on the surface of a plate, and in this case we define what is called surface charge density sigma, and sigma is a Q over A. The unit of sigma is coulomb per meter squared, and if we define here the volume charge density, we have some charges distributed on the sphere, and in this case we can define what's called volume charge density, rho equals Q over V, and the unit of rho is coulomb per meter. Electric field due to an infinite sheet of charges at a point B, distance d from the surface of the plate, and I mean by infinite plate is that the dimension of the plate is larger than the distance of the point P at which we need to calculate the electric field. In this case, using Gauss's law, you can find that the electric field here, it's not required to know how to derive this formula, but all you need to know is that this formula is derived using Gauss's law. The magnitude of the electric field at point B is uniform, which means that if you change the distance d, you will get the same electric field at point B. Is sigma over epsilon over 2 epsilon naught, and sigma is a Q over A. So you'll find that E is a Q over 2 epsilon naught A, assuming that this plate is situated in vacuum. And then as you know, epsilon naught is 1 over 4 by K. You can find the electric field in terms of K as 2 by K Q over A, and then you can calculate the electric field to be sigma over 2 epsilon naught. And now, in order to find the electric field between the two plates, two identical plates, one is charged with a positive charge Q, so it has sigma equals a Q over A, and the other is charged with a negative charge minus a Q, so it has a surface charge density minus sigma equals minus a Q over A, and the two plates are separated by distance d, as I explained in the Zoom meeting I had with you guys. I told you that the electric field to the left of the positive plate will be 0, because to the left of the positive plate we have two fields, one coming from the positive sheet, the other coming from the negative sheet, but they are opposite to each other, and since they are equal in magnitude, they cancel out, and you have a net field to the left of positive Q to be 0. And if you calculate the electric field to the left of the to the right of the negative sheet, again you will find it in the similar fashion to be 0. However, the electric field between the two plates will come from the positive plate and the negative plate. We have two fields, but the two fields are equal in magnitude, but they point in the same direction, and in this case you have to add sigma over 2 epsilon naught plus sigma over 2 epsilon naught, and you will get finally the electric field between the two plates to be sigma over epsilon naught. So the electric field is sigma over epsilon naught, which means that Q over epsilon naught A, 1 over epsilon naught is 4 by K, so you can find the electric field. The electric potential is related to the distance and electric field by this formula, that V equals ED cosine theta. However, E and D are in the same direction, so the angle between E and D is 0, so you will get that V is E times D, and since E is a Q over epsilon naught A, you will find that the voltage is a Q over epsilon naught A times D. Let us take an example here. If we have a square sheet of side length 40 centimeter charged with a charge 32 nanocoulomb. Find what is the magnitude of the surface charge density. Sigma equals Q over A. And if you plug in the numbers, you will get, of course, you know how to find the area of a square. Just you square the side. So you will find that sigma is 0.2 microcoulomb per meter squared. And then determine the magnitude of the electric field at distance 20 centimeter from the sheet. Simply the electric field is Q over 2 epsilon naught A. You will find that the electric field is 11.3 times 10 to 3 Newton per coulomb. Example 6. We have two circular sheets. Each has a diameter 40 centimeter and each has a charge of magnitude of 50 microcoulomb. Calculate the magnitude of the electric field between the two sheets. Simply E equals Q over epsilon naught A, and since the plate is circular, so the area of a circle is pi r squared, and then E is Q over epsilon naught times A. You will find that the electric field at a distance you will find that the electric field between the two sheets will be 45 times 10 to 6 Newton per coulomb. Now, if the distance between the two sheets is 20 centimeter, what is the electric potential? V equals E times D. And then you will find that the potential between the two plates is 90 times 10 to 5 volt. Practice number 4. If the electric field between two pair plates is 4 times 10 to 4 volt per meter and the area of each plate is 0.2 meter square, what is the magnitude of the electric charge on each plate? This you have to do yourself. Let us now work on the capacitor. Simply, as I told you in the video 1, I told you that any capacitor can be built from two identical conductors carry equal and opposite charges plus Q minus Q and separated by a given distance, and this distance is filled with an insulator. And you know what is the difference between a conductor and insulator? The conductor have all the charges on the surface, so the net electric field inside the conductor is 0 at electrostatic equilibrium, while for the insulator the charges are bound. They are not free to move, so you will find that everywhere on the surface of the insulator you have an electric field. Now, here we have two identical conductors. One carries a charge plus a Q, the other carries a charge minus a Q, and separated by a distance D. As you see, we have an electric field originating from the positive plate and terminating on the negative plate, and the functioning of this capacitor is to store charge or electric energy inside the electric field E, filling the space between the two conductors. The capacitor is a component which has the capacity to store energy in the form of an electric charge, producing an electric potential. C equals Q over A, so always the capacitance is the ratio of a Q over V. You should understand that C neither depend on a Q nor depend on V. For example, if I tell you we have a given capacitor and has a capacitance of 1 farad. By the way, the unit of capacitance, as you know, is farad, because 1 coulomb over 1 volt is equivalent to what's called farad, after Michael Faraday, who was the first to use this unit and to measure the capacitance of a given capacitor. Now, if we have a capacitance of 1 farad, this means that if we have 1 volt here, the charge will be 1 coulomb. So 1 over 1 is 1 farad. Now, if we double the voltage, charge will be doubled, because the relationship between Q and V is linear. So if we double V, Q will be doubled, so 2 over 2 you will get 1, and so on. So from this, you should understand that the relationship between Q and V is linear, and the slope of this relationship is the capacitance, and the capacitance neither depend on Q nor depends on V. Now, let us discuss the parallel plate capacitor. I told you this type of capacitor is used to produce uniform electric field, very similar to the electric field that we find in the axons in our neurons, in our nerve system. So here we have two identical infinite sheets of charges. One is charged with a positive charge Q, the other is charged with a negative charge minus a Q, and in between the two places we have an insulator, and the separation between the two places is D. And then if I ask you what are the factors that determine the capacitance, you start with the general formula for the capacitance, C equals Q over V, but as you know, V for uniform electric field is related to the field by ED, and since E between the two places is Q over epsilon naught A, you will get that C is epsilon naught A over D. From this formula you see that C depends on two factors. It depends on the type of the dielectric, and also it depends on the geometry of the two conductors A and D. So the capacitance only depends on the capacitor geometry, and also depends on the type of the insulating material between the two conductors. In this figure, we assume that the space between the two places is filled with a vacuum, and for vacuum we know that epsilon naught is equal to 8.85 times 10 to minus 12 farad over meter. Let us take an example here. Capacitor of charge 4 microcoulomb. This means that each plate, one plate is charged with 4 microcoulomb, the other plate is charged with minus 4 microcoulomb. The potential difference between the two plates is 2 times 10 to 3 volt. What is the magnitude of the capacitance? Simply C equals Q over V, and you can calculate the capacitance to be 2 nanofarad. Example number 9. If we have a parallel-placed capacitor made of two circular plates, one carries a charge plus 4 microcoulomb, the other carries a charge minus 4 microcoulomb, and if the potential difference between the two is 2 times 10 to 3 volt, and if the separation between the plates is 2 millimeter, find the magnitude of the electric field. So V equals ED, E is V over D, and if you calculate the electric field, you will find it is 1 times 10 to 6 volt per meter. This means that if the separation between the two places is 1 meter, the potential difference is 1 million volts. Imagine the high voltage that we can construct between two plates separated by 1 meter. The radius of each plate. Simply, you know that the magnitude of the electric field between two plates is Q over epsilon naught A, and then you can from here calculate A. A is 0.45 meter squared, and then A equal to pi r squared. From here you can calculate the radius of each plate. In a parallel plate capacitor of charge Q, if the plate separation is 0.2 centimeter and the area of each plate is 2 millimeter squared, the potential difference across the capacitor is 2 times 10 to 3 volt. Find the capacitance, the magnitude of each plate charge, and the magnitude of the electric field. Practice number 6. Capacitor of charge 120 microcoulomb at 60 volt. If the potential difference is increased to 100 volt for the same capacitor, what is the magnitude of the capacitor charge at 100 volt? This is